Millennia, the ocean has been the realm of silence, stealth, and slow, grinding motion. Submarines are built to hide, and torpedoes are built to strike quietly. But what if all that changed? What if a weapon could move through the water not at 50 knots, but at over 200 miles per hour, faster than a bullet train, making every known submarine defense system obsolete? This is the story of the technological marvel that dared to defeat the very laws of hydrodynamics. The supersonic cavitation torpedo, often conceptualized as Project Sea Lance or Barracuda, IT was a $900 million military dream, a direct, aggressive answer to the Soviet Union's own terrifying super torpedo, the Shkval. But the American version failed for one crucial, simple reason. It was too fast to control: the bubble of speed. The core genius of the weapon was the concept of supercavitation. This is the process of creating a massive, enveloping gas bubble around the torpedo's body, effectively allowing it to fly through a pocket of vapor instead of fighting dense water. The weapon was literally a missile flying underwater. The friction was reduced by a factor of hundreds, granting it impossible speed, the unstoppable force. A torpedo moving at 200 miles per hour reduces a submarine's reaction time from minutes to mere seconds. No conventional countermeasure, no evasive maneuver, no decoy, no defensive torpedo could possibly keep up. It was designed to be an absolute kill weapon, guaranteeing the destruction of any target it locked onto. The target acquisition window was non-existent. If you saw the Ghost Torpedo coming, you were already dead. The steering nightmare. The fundamental paradox that killed the project was simple physics. The torpedo needed to move in the gas bubble to achieve supersonic speed, but that bubble meant the weapon was never actually touching the water. It couldn't use rudders, fins, or conventional steering. The result was a $900 million, multi-million-dollar rocket that, once launched, was less maneuverable than a thrown javelin. Stay with us as we dive into the insane physics and the fatal engineering flaws of the Ghost Torpedo, because the military created a weapon that couldn't be stopped, but also couldn't reliably find its target. The greatest obstacle to high-speed underwater travel is drag. Water is approximately 800 times denser than air, meaning a typical torpedo must fight immense hydrodynamic resistance, capping its speed around 50 to 60 knots. Supercavitation bypasses this problem entirely, offering a tantalizing route to Mach speeds beneath the waves. The goal is to reduce the friction, drag, by surrounding the entire weapon with a gaseous envelope or bubble. This requires two critical things to overcome the water's density. 1. The cavitator. The torpedo needed a specialized flat-faced or conically shaped nose, known as a cavitator. As the torpedo accelerates, this shape forces the water outward. At high speed, the pressure behind the nose drops so drastically that the water instantly vaporizes, creating a massive bubble that extends the entire length of the torpedo. The torpedo literally flies through its own steam. This nose design was the subject of intense, highly classified research, requiring materials that could withstand the initial, immense pressures of launching the bubble. 2. The gas injection system, to ensure the bubble remains stable and completely envelopes the body, a necessity for maintaining speed. The torpedo needs a powerful, continuous injection of gas. This gas, typically superheated rocket exhaust or combusted fuel vapor, is vented out through the cavitator. This is the ultimate feat of engineering. A torpedo that requires its own onboard rocket engine, not just for propulsion, but also to generate the gas necessary for the stealth and speed bubble. Without the gas, the bubble collapses. Without the bubble, the torpedo instantly decelerates and likely disintegrates due to the shock of impact with the water. The engineering challenge was immense. The torpedo had to maintain a precise angle of attack to keep the bubble stable. If the nose dipped or turned too sharply, the bubble would collapse on one side, and the full force of the 200 miles per hour impact with the water would instantly tear the weapon apart. The slightest deviation from a straight line meant catastrophic, high-speed self-destruction. This requirement for perfect, constant stability directly conflicted with the Navy's strategic demand for a weapon that could maneuver and pursue an evading target. The engineers managed to defeat the water, but they created a new, terrifying problem. How do you steer something that isn't touching the environment it's moving through? The American desire to build the Sea Lance was not born of abstract research. It was a desperate, reactive project driven by the terrifying technological lead held by the Soviet Union. In the late 1970s and early 1980s, NATO naval intelligence confirmed the existence and operational status of the Soviet Va-111 Shkval supercavitating torpedo. The Shkval was a revelation. It proved that the concept was not science fiction and that the Soviets had cracked the core propulsion problem first. The Soviet weapon could achieve speeds of over 200 knots, 230 miles per hour, a staggering speed that completely blindsided and terrified Western defense strategists. The idea that a Soviet submarine could launch a weapon that Western surface ships and attack submarines could not evade, track, or counter created massive panic in the Pentagon. The strategic advantage of speed suddenly shifted the balance of underwater warfare. The Shkval defined the military requirement for the Sea Lance. A speed advantage was mandatory. However, the Soviet design was simple and brutal. It was essentially an underwater rocket. It used a powerful solid-fuel rocket motor for propulsion and ejected exhaust gas through its nose to form the supercavitation bubble. Its guidance was simple, even primitive. It was an unguided or terminally guided weapon, meaning it was primarily aimed before launch and maintained a relatively straight course toward its target. The Soviets, pragmatists in engineering, accepted the massive lack of maneuverability as a necessary, temporary compromise for the strategic advantage of pure speed. The U.S. Navy, however, demanded more from its $900 million investment. The U.S. wanted a super torpedo that retained full mid-course guidance and was capable of making sharp turns to track an evading enemy submarine. The fatal assumption was that American engineering could solve the steering problem that the Soviets had strategically avoided. This demand for high maneuverability, to turn the rocket into a smart cruise missile, is where the $900 million project ultimately sank, as the engineers found themselves fighting the core physical constraints of their own design. The core engineering failure of the Sea Lance was the guidance paradox. A standard torpedo uses movable fins, rudders, and elevators, and often relies on the flow of water over the hull to receive acoustic signals, sonar, and execute turns. The supercavitating torpedo could do none of this. Since the torpedo was enveloped in a continuous gas pocket, the conventional control surfaces were rendered useless. They were simply steering in vapor. The high-speed turn required the application of immense force against the water, but the bubble actively prevented the water from making contact with the control surfaces. Furthermore, the massive acoustic noise generated by the rocket engine and the turbulent, constantly collapsing and reforming cavitation bubble completely drowned out any possibility of using onboard sonar to guide the weapon. The torpedo was deaf, blind, and functionally untouchable by the water. Engineers proposed highly complex and expensive solutions to overcome this. 1. Vectored thrust, using small, powerful, controlled rocket thrusters near the rear of the torpedo to vent gas and force the weapon into a turn. This required extremely fast, complex computer control and massive amounts of fuel, making the torpedo heavier and reducing its effective range. 2. Pressure plate steering. The most aggressive solution involved using small, movable plates or wedges at the cavitator nose. When deployed, these plates would push momentarily against the water, causing the bubble to momentarily collapse on one side and force the torpedo to turn. This maneuver was extremely violent, highly destabilizing to the bubble, and constantly risked total bubble collapse and self-destruction at 200 miles per hour. The computer system required to execute such a maneuver without immediately destroying the torpedo was beyond the practical limits of 1980s era miniaturization and processing power. The complexity of these required solutions was crippling. They had created a weapon that could go from 0 to 200 miles per hour instantly, but could only travel in a mostly straight line. The U.S. Navy demanded a guided missile. The laws of physics delivered a hyper-fast, very expensive, unguided bullet. The final nails in the coffin for the Sea Lance project were logistical and financial. The requirement for extreme speed and advanced, exotic materials pushed the unit cost of each torpedo to an astronomical and eventually unsustainable level, contributing to the estimated $900 million total project cost. Point 1. The rocket motor cost and handling. Unlike conventional torpedoes, which use quiet, reliable electric or auto fuel engines, the Sea Lance required an immensely powerful, high-pressure, complex solid-fuel rocket motor capable of generating the necessary thrust and the cavitating gas. These motors were single-use, extremely difficult to handle and store on a submarine due to the inherent volatility of rocket propellants, and prohibitively expensive to manufacture and maintain. They were not just propulsion, they were volatile munitions. Point 2. Submarine modification. Conventional torpedo tubes were designed for low-pressure, slow-eject mechanisms. They were not designed to handle the explosive, high-pressure launch required for the Sea Lance. Every submarine would require expensive, complex upgrades to its launch tubes, fire control systems, and internal storage areas to safely carry the Ghost torpedoes. This added billions to the overall fleet cost, spreading the $900 million failure far wider. Point 3. The risk versus reward. Ultimately, the Navy had to justify a massively expensive, high-risk, functionally unguided torpedo when their existing, quieter Mk-48 torpedoes were already highly accurate, fully guided, and devastatingly effective against Soviet submarines. The Mk-48 could be fired from a great distance and guided over complex courses. The Sea Lance required the submarine to get dangerously close to the target to ensure an effective hit, an unacceptable risk for a nuclear attack submarine whose primary defense is stealth. The cost and risk outweighed the marginal strategic gain of speed, especially when that speed came at the expense of guidance. The project was canceled in the late 1980s. The military concluded that the weapon was strategically redundant, existing weapons were good enough, and technologically unviable. The steering problem was insurmountable without revolutionary material science. The terrifying dream of a supersonic underwater missile was buried, leaving behind only the lessons of physics that define the true limits of speed in the deep ocean. But the failure of the American torpedo did not end the supercavitation arms race. The lessons learned were immediately adapted into a more conventional, equally terrifying use for underwater speed, a use that continues to push the boundaries of naval warfare today. The supercavitation bubble was the key to speed, but it also introduced a colossal, debilitating engineering challenge: terminal heat and material science. To maintain the gas bubble, the torpedo had to generate immense internal heat and survive the friction of the high-speed vapor layer. The water friction alone, even at 200 miles per hour in a vapor envelope, was enough to subject the cavitator and the forward hull section to extreme thermal stress. The heat generated at the cavitator's edges, where the high-pressure water was forced away, was enough to constantly threaten the structural integrity of the nose. If the cavitator failed due to heat stress, the bubble would instantly collapse, and the entire torpedo would shatter on impact with the dense water. Furthermore, the rocket motor, running at maximum power to maintain both thrust and the gas bubble, generated immense heat internally. This heat had to be actively managed to prevent the fuel from prematurely igniting or the internal electronics from melting. The engineers required exotic, aerospace-grade materials, specialized titanium alloys, and advanced composites. They were capable of withstanding both the violent heat of the rocket engine and the extreme erosive forces where the bubble met the water. These materials were prohibitively expensive, difficult to work with, and added to the already astronomical unit cost of the torpedo. The cost was not just the rocket motor. It was the cost of building a weapon whose structural integrity was constantly on the verge of thermal and mechanical failure. The American team spent millions trying to perfect the nose material that would neither melt under the intense heat nor erode under the high-speed impact forces. The Ghost Torpedo was a paradox, a high-performance heat engine designed to fly through the coldest, most unforgiving environment on Earth. This constant struggle against heat stress proved that the weapon's service life, even if fully operational, would have been tragically short. The fundamental purpose of a submarine is stealth. Submarines hunt and survive by listening. The American Ghost Torpedo, designed to be the ultimate anti-submarine weapon, was the antithesis of stealth. Its defining feature was its catastrophic, overwhelming noise signature. The propulsion method alone, a solid-fuel rocket motor burning at full thrust, generated noise levels that were immense. But the true acoustic nightmare came from the supercavitation bubble itself. The bubble is not a stable, smooth pocket of vapor. It is a chaotic, turbulent boundary layer where water is constantly vaporizing and collapsing. This process generates massive amounts of high-frequency noise and vibration. The sheer volume of noise meant that the launching submarine, the moment it fired the sea lance, would instantly surrender its own position. The noise of the torpedo would travel hundreds of miles through the water, making the launching submarine a prime, easily tracked target for the enemy's counterattack. The use of the Ghost Torpedo was an act of tactical suicide. Furthermore, the noise made the torpedo itself acoustically blind. As we discussed, the massive bubble noise completely masked the torpedo's own sonar systems, making any mid-course guidance impossible. The weapon was deafened by its own engine. The very speed designed to guarantee a kill also guaranteed a tactical failure of stealth and guidance. The Navy realized that the trade-off was unmanageable. What good is an unstoppable weapon if its use instantly kills the launching platform? The solution devised by engineers to counter this noise was an equally insane idea, requiring the torpedo to briefly abandon its own bubble mid-flight. The engineer's final, most desperate attempt to solve the guidance paradox involved a terrifying, high-risk maneuver: the momentary bubble collapse and re-establishment. Since the torpedo was blind and unsteerable inside its bubble, the theory suggested that to acquire the target or execute a necessary turn, the torpedo would have to momentarily shut down the gas injection and intentionally allow the supercavitation bubble to collapse on the control fins. For a fraction of a second, the conventional fins would touch the water, allowing the computer to execute a tiny, high-speed correction. Immediately afterward, the gas injection would have to fire again at maximum power to reform the bubble and re-establish the supersonic speed. This was a nightmare of physics and engineering precision. The speed of the torpedo meant that the moment the bubble collapsed, the water would strike the hull with the force of a high-caliber impact, threatening to rip the unshielded body apart. The electronic sensors would experience violent shock. The computer system would have to calculate the precise moment of turn, the exact duration of the collapse, and the perfect reignition sequence, all while traveling at hundreds of miles per hour. A mere millisecond of error meant the loss of a multi-million-dollar missile. The technical requirements for the computer, the speed of the valve actuation, and the structural resilience of the hull were all beyond the practical reach of 1980s technology. The system would have been too complex, too delicate, and too prone to failure. The constant, terrifying risk of self-destruction during the guidance correction made the weapon fundamentally unreliable. The Ghost Torpedo was a weapon that required its own demise to be guided, an unacceptable trade-off that proved the physics of speed and guidance were mutually exclusive. The ultimate cancellation of the Sea Lance project in the late 1980s was a victory of practicality over ambition. The Navy determined that the $900 million investment could not be justified against the performance of their existing, quieter, and highly maneuverable Mk-48 torpedoes. The Mk-48 had achieved a level of technological sophistication that negated the raw speed advantage of the Sea Lance. The Mk-48 utilized wire guidance, allowing the launching submarine to actively steer the torpedo in real time, receiving acoustic data through the wire link. It was a smart weapon capable of complex, evasive maneuvers and retargeting. The Sea Lance, by comparison, was a fast, dumb bullet. Furthermore, The end of the Cold War rapidly eroded the urgency required to justify the astronomical spending on the Ghost Torpedo. The threat of a massive Soviet submarine assault diminished, making the necessity of an immediate kill anti-submarine weapon less critical. The defense budget, now under heavy scrutiny, could no longer tolerate a $900 million project that was technically brilliant but operationally flawed and financially unsustainable. The assets developed, the specialized rocket motors, the advanced cavitator designs, and the exotic materials research were not simply scrapped. They were absorbed into highly classified naval research programs. The knowledge gained from Project Sea Lance became the foundation for future, smaller, supercavitating projectiles designed for defensive measures, where the need for maneuverability was less critical. The failure of the large torpedo concept fueled the success of smaller, short-range hyperspeed rounds. The Ghost Torpedo was a strategic failure, but its components became the silent legacy that continues to influence naval defense strategies today, ensuring that the dream of underwater speed never fully died. The most tangible, non-classified legacy of the Sea Lance project is found not in a sunken submarine, but in massive, specialized research facilities. Supercavitation water tunnels test the integrity of the cavitator and the stability of the gas bubble. Engineers had to build colossal hydrodynamic test tanks and tunnels capable of generating water flow speeds comparable to the torpedo's speed. These facilities, primarily at the Applied Research Laboratory, ARL, at Penn State, became the only safe place to study the extreme physics of the Ghost Torpedo. These water tunnels allowed scientists to observe, through high-speed cameras, the precise dynamics of the bubble formation, the effect of different nose shapes, and the chaotic instability caused by attempts to steer. The tunnels confirmed the engineers' worst fears. Maintaining the bubble stability during anything other than a straight line was nearly impossible. The moment a force was applied to turn the torpedo, the bubble would instantly collapse on the inside curve, subjecting the hull to immense, asymmetrical forces guaranteed to cause a structural breakup. The millions spent on these facilities were not wasted. The research into supercavitation physics profoundly advanced the understanding of turbulent fluid dynamics and drag reduction. While the large torpedo failed, the knowledge gained laid the groundwork for future applications, including high-speed propulsion for small craft and, ironically, in the civilian sector for high-speed propellers and pump designs. The canceled $900 million project ultimately served as the most expensive, yet most crucial scientific experiment into the limits of underwater speed. It proved definitively that the technical leap required to go from a fast, unguided rocket, the Soviet model, to a smart, maneuverable weapon, the American demand, was a chasm too wide for 1980s technology to cross. The Ghost Torpedo was technologically possible, but operationally impossible, a silent, fast-moving warning of the true, permanent power of the deep ocean. The $900 million failure of the Sea Lance was not a complete loss. The research conducted by the Applied Research Laboratory into supercavitation physics pushed the boundaries of high-pressure hydrodynamics further than any other military project before or since. The lessons learned from the Ghost Torpedo, specifically how to initiate, maintain, and stabilize a massive gas bubble, were immediately transferred to smaller, more feasible applications. One of the most profound legacies was the improvement of propeller and pump design across the entire Navy. The engineers discovered precisely how to delay or mitigate unwanted cavitation, the destructive, efficiency-killing process that erodes ship propellers and water pumps. By understanding the mechanisms that created the massive bubble on the Sea Lance, they learned how to prevent the tiny, destructive bubbles that damage conventional equipment. The failure of the offensive weapon led directly to the quiet, long-term efficiency gains across the entire naval fleet. More dramatically, the propulsion and gas injection techniques developed for the large torpedo were scaled down and adapted for defensive countermeasures. Why build a full-scale, unguided missile when you can build a small, high-speed projectile? The technology transitioned into creating hyperspeed rounds and decoys. These smaller projectiles, designed for extremely short range, defensive deployment, used supercavitation to achieve impossible speeds, but their lack of guidance was accepted because their mission was simple: to disrupt an incoming enemy torpedo or create a short-lived acoustic decoy. The Sea Lance may have been too big and too expensive to fly, but its core technology continued to live in the shadows, creating a new, niche field of high-speed underwater combat. The fundamental trade-off remained. Speed comes at the cost of control, but for specialized defensive rounds, that trade-off was finally acceptable. The failure of the torpedo to become a smart missile drove the military to a critical, long-term strategic decision that forever changed how the U.S. Navy views underwater engagement. The cancellation of the Ghost Torpedo marked a crucial, definitive strategic choice by the U.S. Navy. Guidance and stealth would always triumph over raw speed. The core of the decision lay in the comparison between the Sea Lance and the existing, highly maneuverable Mk-48 ADCAP, Advanced Capability, torpedo. The Mk-48 utilized wire guidance, a thin wire that unspooled behind the torpedo, allowing the launching submarine to monitor the torpedo sonar, process the data, and actively send course corrections in real time. This made the Mk-48 an incredibly smart weapon, capable of complex evasive maneuvers and retargeting after launch. The Sea Lance, even at 200 miles per hour, was a straight-running weapon that required the submarine to get dangerously close to the target for a guaranteed hit. The moment the launching submarine breached its stealth barrier, by making aggressive maneuvers or simply being detected, it was vulnerable. The Mk-48, however, could be fired from maximum standoff range, allowing the launching submarine to remain silent, deep, and hidden. The Navy concluded that the ability to remain hidden and guide a weapon over a long, complex course was infinitely more valuable than achieving a kill in the last few seconds. A fast torpedo that reveals your position is a massive liability. A slower, quieter torpedo that guarantees the kill from 50 miles away is the ultimate strategic asset. The $900 million project was a failure because it tried to solve a tactical problem, speed, without respecting the strategic laws of submarine warfare, stealth, and range. This final, decisive commitment to smart, quiet weapons over reckless speed solidified the fate of the Ghost Torpedo, but left the engineers with a bizarre, enduring problem: what to do with the highly toxic experimental rocket fuel. The solid fuel rocket motor required to power the Sea Lance was not only immensely powerful, but also contained highly specialized, volatile, and toxic propellants, a necessary byproduct of creating the gas required for the supercavitation bubble. The cancellation of the program left the military with large stockpiles of these experimental rocket motors and the raw propellant mixtures. Disposing of this material was a massive, expensive, and environmentally hazardous undertaking. The fuel components were often chemically unstable and required highly controlled incineration or long-term sequestration. Unlike conventional military waste, the supercavitation propellants were unique and tailored for extreme performance, meaning they could not simply be mixed with standard missile fuel for disposal. This created a logistical and financial liability similar to the one that plagued the floating nuclear plant. The $900 million failure was not just a theoretical loss. It was a physical legacy of toxic, expensive waste that required years of dedicated effort to neutralize and permanently bury. This logistical tale reinforced the Navy's decision to abandon the technology. The operational cost of the torpedo included not just the launch price, but the hidden, long-term cost of maintaining and eventually disposing of a highly specialized, volatile weapon system. The quiet, electric motors of the Mk-48 torpedoes, by contrast, presented a far cleaner, cheaper, and safer long-term logistical profile. The Ghost Torpedo was defeated not just by physics, but by the relentless scrutiny of environmental and budgetary reality. While the U.S. Navy abandoned the Sea Lance project, the concept of supercavitation did not die globally. The technology, driven by the original Soviet Shkval and subsequent Russian research, continues to be a factor in modern naval warfare, proving that the threat the Sea Lance was designed to counter remains real. Russia has continued to refine the Shkval design, accepting the trade-off of poor maneuverability for immense, sudden speed. The modern versions of the Super Torpedo are essentially point defense weapons, designed to be launched when the enemy is already close, guaranteeing a hit regardless of evasive maneuvers. The sheer terror of this weapon ensures that naval commanders must constantly factor in the possibility of a super-speed underwater ambush. Furthermore, China and Iran have invested heavily in their own supercavitating weapon research, viewing it as a viable way to defeat the advanced anti-torpedo and decoy systems used by Western navies. The technology remains controversial because of the high acoustic signature and lack of guidance, but its raw, overwhelming speed is the ultimate countermeasure to the modern submarine's greatest asset, stealth. The Sea Lance, though never built, continues to influence the U.S. Navy's defensive strategies. The Navy invests heavily in countermeasures designed to confuse or evade supercavitating weapons, including hypercomplex acoustic decoys and specialized launch systems. The Ghost Torpedo is a weapon that was canceled, yet its conceptual existence continues to drive billions of dollars in defensive spending, solidifying its place as one of the most important never-built projects of the Cold War. The final irony of the Ghost Torpedo is the profound ethical question it poses about the future of warfare, a question that remains completely unanswered. The supersonic cavitation torpedo, the Ghost Torpedo, was a perfect example of technology reaching a point of strategic redundancy and ethical failure. The engineers proved they could break the speed barrier underwater, but they could not break the barrier of control and stealth. The project forced the military to confront a profound question. Does absolute speed, even if unguided, grant an unacceptable advantage? The answer for the American military was a strategic no. They chose the smart, quiet, ethical kill over the noisy, high-risk, catastrophic kill. The Mk-48, with its slower speed but perfect guidance, represented precision and restraint. The Sea Lance represented reckless, uncontrollable power. The $900 million was spent to learn that the laws of physics, specifically the guidance paradox, define the permanent limit of underwater missile technology. The speed necessary to form the bubble makes the weapon acoustically blind and hydrodynamically unsteerable. This simple physical constraint proved that not every technological dream is worth pursuing, especially when the solution is more dangerous than the problem itself. The Ghost Torpedo was the fastest weapon ever conceived to travel in a straight line, a $900 million solution to a problem that couldn't be solved without risking the entire submarine fleet. The U.S. chose guided stealth, Mk-48, while Russia chose unguided speed, Shkval. Given that military AI is rapidly advancing, do you believe future supercavitating torpedoes will use advanced AI and microthrusters to finally solve the guidance paradox? Or will the laws of physics, the noise, and the bubble collapse always make the Ghost Torpedo a technologically unusable weapon? Let us know your predictions for the future of supercavitation in the comments below.